FPGA transfers our T developed and the status about porting them to the Jasper Toolflow. Quick outline. 4 FPGA transfers will be introduced, and then I will talk about the yellow blocks we have done and how to do multi-clock design by using the Toolflow. I believe many of you have known Snap2 is a powerful platform targeting on the Kintex UltraScale 7 FPGA, and it has more than 5,000 DSPs and 2,000 VRAMs. The out-chips memories include QDR and DDR, and to make it flexible, it has 2 FMC connectors and several ZD connectors. Just like Jack said, customer hardware includes a series of ADC cards based on the ZDock connectors. We also developed a series of ADCs based on the FMC connectors. They can be, they have different sampling rates and different data resolution to meet the different requirements. We also developed 2 DIC cards. They have been used in the Corten computing system. These are 3 expansion boards. They can be connected to Snap2 through the ZD connectors. The left one is full of QSFP plus connectors to expand the bandwidth. And the middle one has an extra PCIe connector. So the Snap2 can be connected to a CPU server, and it has been used to accelerate the AI application. And this one is FMC expansion board to increase the off-chip memories. Okay, about the structure. Snap2 is a 6U standard size, so it can be plugged into a 2U cabinet like this. If several boards you are used, we suggest to plug them into a 9U cabinet like this. Besides, we designed a liquid cooling structure like this. Look at the photo. The FPGA boards are put into the box, and the box are full of liquid. There is a pump to make the liquid to leak between the box and the cooling fan, so to improve the heat dissipation to reduce noise and electromagnetic interference. Our next generation board is Snap3. The architecture is similar to Snap2, but the chips on the board can be VU9P or VU13P. The blank PCB board is available since last year, but the FPGA chips is too expensive, so we may be to assemble one board this year and do some testing. Besides, we also developed 2 much cheaper platforms. They are Kintex 7 boards. These boards are PCIe standard size and only half of the Snap2. For the version 1, it has a FMC connector, so this board can be compatible with all the FMC cards we have made. This is the version 2, have 4 ADC chips on the boards, and these ADCs have very good synchronization. In one application, we do the synchronization between about 500 inputs. Okay, next is about the yellow blocks we have done. Besides the Snap3, the other 3 platforms have been ported to Jasper Toolflow, and of course the 1 gig Ethernet and the 10 gig Ethernet are available. And the 3 kinds of ADC cards has also been ported to Jasper Toolflow. The first one is the E2V1, and the maximal sampling rate is 5 gigahertz. It has been used in the first backend and the music correlator. The second one is the one has very good synchronization. The maximal sampling rate is 500 megahertz, and the data resolution is 12 bits. It has been used into the 21 CMA correlator in China, no, beamformer. The third one is the HMCID. There are 16 inputs, and each is 250 megahertz, 8 bits. It's been used in Tianlai beamformer. We also made a GPS yellow box to capture the absolute system trigger time to get the polling size 10 delay compensation and the phase delay compensation when overseeing the sound. You can download ORIS from my personal repository or from Casper SGL repository, Snap2 branch. About the applications based on the hardwares and Jasper, please see tomorrow's talk by my colleague Zhao Lantian. Okay, next I will talk about how to do a multi-clock design. Look at these two fingers. They show the resource utilization of two different applications. The left one is to do the beamformer and the correlator on just one step 2 bird. The input is from the 10 gig Ethernet. So load the AIoT RAMs and the BRAMs is nearly full, but after regular optimization, the timing is good. But for this one, the input is from the ADC. If only one processing clock for the user logic, no matter which, the timing is always a problem because some parts can't meet the requirement of setup time. So what results in the bad timing? I think there are two challenges. One is the resource utilization is high, and the other is also the important one. Because the ADC cards are plugged into the FMC connectors, and the two FMC pins are mapped to different dies, and they have to be. As we all know, the FPGAs are becoming more and more powerful, but most of them are consist of several dies. So the place and the routing is becoming harder than just one die. So our solution to observing timing for the application tool is to do a multi-clock domain design for the user logic. And I also have to manually modify the user clock of the yellow blocks on the top file. This is an application diagram. I divided them into 3 clock domains. The ADC and the FPGA's clock is equal to the sampling clock. Because the input is real data, so the only half of the PFB output is needed. So the beamforming clock can be decreased to only half of the sampling clock. Besides, the beam coefficient update period is about 1 minute, so the update clock also can be slowed down. Okay, after design the different clock domain, the first step is to transfer data between different clock domains. Generally, we use register, FIFO, or RAMs to make it because the write and read clocks can be different. But in the Simulink, we cannot set the clock directly because the clocks are inferred from the inputs. For the later part one, there are 2 kinds of inputs. One is the address from a counter. So we need to set the sample period source of the counter to be inferred from the inputs, but not this. The other is constant. We should not select sampled constants. For the red parts, the clock are inferred from the input yellow blocks. So the next step is to set the correct sample rate of the yellow blocks. In my application, I set the sample rate to be 1, 2, 3 to represent 3 different clock domains. Then the last step is to select the needed user IP clock sources. Because so far the punch for yellow block only supports one IP clock IP sources, so I need to manually modify the use clock of the yellow block to be use clock -1, use clock -2, use clock -3. So then the multi-clock design is done. Okay, in the conclusion, in this talk, 4 FPGA parameters are introduced and the 3 are reported to Jasper Toolflow. And the 3 kinds of ADC are built to be yellow blocks and are used in different applications. Also, GPS yellow blocks is available to get the absolute system trigger time. And some tips on the multi-clock design for the used logic are shared. Okay, the last is an advertisement. If you are interested in the hardware, please contact me. That's all. Thank you.